Hi folks, it's Dr. P. This video helps to give you some more practice with adding signed binary numbers of fixed width. Adding is a very basic arithmetic function, but it's extremely important. You're probably very comfortable adding numbers in base 10, but while adding in binary uses the same principle, it's a different number system, so it can be tricky at first. Also, because we're dealing with a function that will ultimately be carried out in hardware, we need to be aware of something called overflow. I've made a video explaining overflow, so make sure you watch that after you finish this video, if you haven't done so already. Why do you need to know how to add in binary? Adding is an extremely important part of computer and microcontroller processors. The arithmetic and logic unit in any computer or microcontroller is going to have an addition unit. Addition is used to add, it can be used to subtract, and it's also used to multiply. It's also used behind the scenes in many other CPU functions, such as determining if a conditional instruction was met or branching to another point in computer memory. So while you might think of addition as being something easy that you learned in grade school, it's actually a really powerful arithmetic function. To start our understanding of addition, we need to understand the truth table for addition. A truth table gives us all of the different possible things that we could be adding together and then tells us what the result is going to be. When we add one bit at a time. So our truth table shows us what we need to do for each bit. If I add 0 plus 0, I get 0. If I add 0 plus 1, I get 1. If I add 1 plus 0, I get 1. If I add 1 plus 1, I get 2. But wait, we can't use the number 2 in binary. So what do? Well, 2 in binary is 1, 0. Let's break down 1, 0 into 2 bits. The LSB is 0, so that would be our sum. The MSB is 1, so that's called a carry. Therefore, we say that 1 plus 1 is 0 with a carry of 1. Our truth table for addition, therefore, looks like this. This truth table is great, but it only works when I'm adding 1-bit numbers together. And odds are good that I'm not going to need to use a calculator or a computer to add 1 plus 1. We need to find a way to expand this to add 2 numbers together that have as many bits as we need. Therefore, we need to understand that while we're adding 2 1-bit numbers together at a time, we could have had a carry from a previous column. So we need to consider what happens with both with and without a carry in term. So our truth table now includes a carry term. Adding 0 plus 0 with no carry is 0. 0 plus 1 with no carry is 1. 1 plus 0 with no carry is 1. 1 plus 1 with no carry is 0, with a carry out of 1. 0 plus 0 with a carry is 1. 0 plus 1 with a carry is 0, with a carry of 1. 1 plus 0 with a carry is 0, with a carry out of 1. And 1 plus 1 with a carry is 1, with a carry of 1. So now that we understand this truth table for addition, we can tackle any addition problem regardless of how large our binary numbers are. But before we do any examples, we need to understand the caveats of adding numbers together. First, I need to remind you of the importance of knowing the number of bits your system will be constrained to. If you're adding on a homework question or an exam, then I would tell you how many bits your system is. Otherwise, you need to understand the limits of your hardware. You need to make sure that the number of bits you use in your arithmetic is equal to the number of bits in your system. I discussed this topic in the 2's complement video and in the overflow video. Make sure you watch those if you're not really sure what I mean by number of bits. Second, we need to understand that when we're working with a fixed bit width system, there's a limit to how big and small our numbers can be. So for example, if we have a 4-bit number system, the biggest number is going to be positive 7, and the smallest number is going to be negative 8. So if I want to add 5 plus 6, I know that the result is not going to be correct in a 4-bit system. While both 5 and 6 can be represented as 4-bit 2's complement values, their sum, 11, cannot be. This is called an overflow. I talk about overflow in a lot more detail in the overflow video, so make sure that you watch that after this video if you haven't seen it already. So it's not just okay to add two numbers together. We also need to be able to interpret the results and see whether or not there was an overflow. In signed binary addition, overflow occurs if we add two positive numbers and get a negative result, or if we add two negative numbers together and get a positive result. It is not possible to get an overflow if we add a positive to a negative or a negative to a positive. How do we check if a number is positive or negative? We look at the sign bit. Third, we need to know what to do with all of our carries. If I'm adding two 8-bit numbers together and wind up with a carryout in the 8th column, what does that mean? Well, it doesn't actually mean anything, and we can totally ignore it. I like to think of doing 2's complement arithmetic as like old maps from before humans knew that the Earth is round. Back in those days, people thought that if you reached the end of the Earth, maybe you'd fall off and get eaten by a dragon. Think of anything that happens to the left of our last bit as falling off of the edge of the Earth. Any carryout terms that are generated are going to fall off the edge of the Earth and get eaten by dragons. A common mistake is that students think that carryout terms means there's an overflow. That is categorically incorrect in signed addition. Nope, that carryout got eaten by a dragon. That's all that happened to it. Now that we have the logistics out of the way, let's do some examples. Let's start with a 4-bit system. Say I want to add -5 to +6. We must start by representing both of these numbers as 4-bit 2's complement numbers. So with -5 plus +6, now that I've converted both numbers to 2's complement, I start with my LSB column. 0 plus 1 is 1. Move to the next column. 1 plus 1 is 0 with a carry. Move to the next column. 1 plus 1 plus 0 is 0 with a carry. Move to the next column. 1 plus 0 plus 1 is 0 with a carry. And that last carry, it falls off the edge of the Earth and gets eaten by a dragon. Goodbye, carry. Does our answer make sense? Absolutely. We know that -5 plus +6 equals 1. And our answer is indeed +1. So that's great. See, the carryout absolutely did not mean an overflow. Our answer is perfectly valid, even though it had a carryout in the last column. Let's say we're working with 8-bit binary numbers. I want to add 86 and -100. First, I need to generate two 8-bit 2's complement values. Having done that, I do the same procedure. I start in the rightmost column, add, and keep on moving until I've run out of columns. 0 plus 0 is 0, no carry. 1 plus 0 is 1, no carry. 1 plus 1 is 0 with a carry. 1 plus 0 plus 1 is 0 with a carry. 1 plus 1 plus 1 is 1 with a carry. 1 plus 0 plus 0 is 1, no carry. 1 plus 0 is 1, and 0 plus 1 is 1, again, no carry. How do we check to make sure our answer is correct? So I don't know about you, but I'm not the greatest at just being able to look at a 2's complement number that's negative and being able to quickly figure out what the magnitude is. Positive numbers, I can easily convert to decimal and double check, but negative numbers takes a little bit of work. So in order to double check your result, if you got a negative result that's in 2's complement, you're just going to do the opposite procedure that you did when you created the 2's complement number. So you start by subtracting 1, and then you flip all of the bits. So if I got the number 14, it means that the result of this addition is -14 in decimal. Does that make sense? Well, yeah, because if I take 86 and I add -100 to it, I would expect my result to be -14. So good. Last, let's do an example with overflow. In a 6-bit system, add +24 and +18. We start with our two 6-bit 2's complement numbers. Start in the rightmost column and keep on going. 0 plus 0 is 0, no carry. 0 plus 1 is 1, no carry. 0 plus 0 is 0, no carry. 1 plus 0 is 1, no carry. 1 plus 1 is 0 with a carry, and 1 plus 0 is 1. See how there was no final carry out? But we got an overflow. Carries have nothing to do with overflow. This overflowed because we added a positive number to a positive number and got a negative result. Sign is everything. I'd like to discuss one more topic. What happens if you need to add a whole bunch of numbers together? Our example so far only had 2 numbers added together. But what if we needed to add 3 or 4 or 5 or more numbers together? In hardware, we would do this by adding numbers together in a sequence. So we'd start by adding the first 2 numbers, getting a result, add the third number to this result, and get a new result. Add the fourth number to that, get a new answer, and so on. That is exactly how I suggest that you add numbers together. Do not try to add several numbers together all at once. It's a real pain to keep track of all of those carries. And really, it's a good idea to add like computers add, because then when you start to design computers or computing systems, you have a better feel for how they work. Okay, folks, hopefully you feel pretty good about adding 2's complement numbers together. If not, keep on practicing. Until next time, stay well.